So welcome to this video, which runs through the worked solutions to the practice assessment for Expressions and Functions Assessment Standard 1.2. Now, question 1 presents us with two right-angled triangles. We've got some of the sides filled in and we're asked to find the exact value of sine x minus y. Notice we're looking for the exact value here, so any decimal approximations will not be suitable. Sine x minus y you should recognise as one of the addition formulae, which are on your formula sheet, and they can be expanded out in this way. So sine x minus y can be written as sine x cos y minus cos x sine y. Now, if we have a little look at our triangles, we don't have that much information yet about the right angled triangle which has x in its angle, but we do have two of the sides in the triangle where y is positioned, and a little bit of Pythagoras will allow us to work out the missing sides here. Now, you can key in 20 squared, 15 squared, add them and find the square root. That will give us your hypotenuse there, although you might also be familiar with the 3, 4, 5 Pythagorean triple, and this triangle here is actually just a multiple of that triangle, where all the sides have been multiplied by 5, which means that 5 5s gives us 25 as the hypotenuse. That hypotenuse shared across the other triangle here, the upper of the two triangles, and it's another Pythagorean triple actually, but you could use your calculator to work out the missing side length on this triangle is 24. So that now allows us to fill in values for sine x and cos y, etc. Sine x would be opposite side divided by hypotenuse, so 24 is the opposite to x there, hypotenuse of 25. And that's going to be multiplied by cosine of y. Cosine is adjacent over hypotenuse, so 20 over 25 in here. And from that we're going to subtract the cos of x, so adjacent is 7 over hypotenuse of 25, and that multiplied by sine of y, which is opposite of hypotenuse in this triangle here, 15 over 25. Now, you could work your way through the fractions if you wanted, but since we have a calculator available, you can key that whole thing in, and we find the exact value of sine x minus y is represented by 3/5. And that's that question finished. On to question 2 here. A little bit of thinking needed, but as long as you go down the right road and remember some key facts, then you should be okay. This is a show that question, a sort of proof type question, where we're trying to demonstrate that the expression here on the left hand side can be transformed into what's on the right hand side. Notice we've got an equivalent sign here. So we're trying to show that 2 sin x minus cos x multiplied by 2 sin x plus cos x is equal to this thing. Now, you might be able to spot that this is a difference of two squares. Both the brackets are the same, the only difference is the signs, which would lead you quite quickly to a simplified expression for that. But if you hadn't spotted there was a difference of two squares, then you would be multiplying out these two brackets. So 2 sin x multiplied by 2 sin x gives you 4 sin squared x. Multiplying 2 sin x by cos x, it's going to give us positive 2 sin x cos x. Multiply these inners, minus 2 sin x cos x, and you'll see these two will cancel, and that's what's going to leave us with this difference of two squares. Finally, minus cos x multiplied by cos x minus cos squared of x. I should just point out here that cos squared of x and sine squared of x as well is just another way of writing cos x or sine x all squared. It's a shorter way of writing it, so don't let that put you off. Now, carrying on with our simplification here, we end up with 4 sine squared x minus cos squared x, and it can be quite tricky here to think, well, where am I going to go next? So a good idea is to look at the result that you're aiming for, and you'll see there that we've got another sine squared term seems to have appeared in the cos squared x term, has gone. So you're thinking perhaps, is there something I can do to get rid of this cos squared x term? And there is, but it relies on you remembering this relationship, which is something you would have seen at National 5, and something that you need to try and remember for higher. Sin squared x plus cos squared x is equal to 1, and so there's a few different ways that you can use this. If you rearrange it, then we can see that cos square of x is in fact equal to 1 minus sin square of x, which means that minus cos square of x, which is what we've got here, would be equal to the negative of this, or you could just substitute in for cos squared x here, and the negatives will eventually take care of themselves. Cos squared x in a bracket, because we're substituting in more than one term, the bracket's essential here, 1 minus sin squared x. Continuing this through, removing the brackets, we've got a minus 1, and we'll actually have a plus sin squared of x, and maybe you can see now we're going to get our 5 sin squared x, and there's the minus 1. So we've managed to, through algebraic manipulation, multiplying out, simplifying, and then making this substitution. It's very important that you try and remember that. We've managed to show that these two expressions are in fact equivalent. So we've done what we were asked. As required, always nice, put a little happy face. Question 3 missing. I think we can find question 3 reasonably quickly. There it is there. It's a wave function type question. So we're going to drag that one into the drawing package. Paste them in here. Yep, let's enlarge that canvas. Great, and hopefully we can now start to work on question 3. Express 2 sin x plus 5 cos x in the form k sin x minus a. So this is the clue here that we're going to be trying to rewrite this basically in a different form. And k sin x minus a, that leads us to addition formula. There's an expansion that we can use here. So k sin x take a, well, that can be written as k sin x cos a minus, and very important, that k multiplied across the second term as well, k cos x sin a. And certainly what I like to do at this stage is have a little look at the original expression here and ask myself what was multiplied by sin x. That's a 2. So I'm going to try and look at this term as isolate sin x and ask myself what is multiplied by sin x here, and it is in fact k cos a. All of that is multiplied by sin x. You don't have to put it in brackets, but it's just making it really clear when it comes to comparing the coefficients in this term, sin x multiplied by 2, in this expression sin x multiplied by k cos a. Do the same thing on the second part of the expression here. Have a look and see what's multiplied by cos x, and in this case it's k sin a. And then that perhaps makes it a little bit easier to compare what's multiplied by cos x down here with what's multiplied by cos x up here. It's a 5. Now there's only one little issue, and that's the fact that this is a plus 5, this is a minus k sin a, but we'll be able to deal with that further down in the working. So comparing the coefficients of these two expressions allows us to say that k cos a from here is in fact equal to 2, and that k sin a from this one here is equal to, now be very careful because of the conflict of signs here, it's not equal to 5, it's actually going to be equal to minus 5. And let's just draw a little 4-quadrant diagram just now. Because we've got two little trig equations here. The cosine one is positive, so that gives solutions from the first and fourth quadrant. The sine one is negative, which takes solutions from third and fourth. And ultimately, when we work out this value of A, which is an angle, we'll be needing to get a solution from the fourth quadrant. Now to calculate K, we use Pythagoras, squaring and adding, taking the square root. So 2 squared 4, 5 squared, or minus 5 squared is 25. We're looking at the square root of 29. And obviously I'm not going through the proof of why this is all working, but if we want to find A, then we need to take the inverse tan of, and remember, tan is equal to sine over cos. You know that from National 5 as well, but that's what we're using, this relationship, tan x is equal to sin x over cos x. That's what allows us to solve for this angle here. So don't forget, you must get this the right way around. Sin x was minus 5, so minus 5 over 2. Negative ratio here, so actually we're going to find the first quadrant angle first of all. And the first quadrant angle is the inverse tan of normal 5 over 2, so just positive 5 over 2. The inverse tan of 5 over 2. This question was in degrees, wasn't it? Yep. Just checking it wasn't in radians. Gives us 68.2 degrees. That's the first quadrant angle. But as we saw earlier, our answer is actually going to come from the fourth quadrant, which is found by doing 360 minus this first quadrant angle. So our value of A is going to be 360 minus that first quadrant angle, gives us 291.8 degrees. And it's good practice here now just to summarise all that. We've managed to say that expression we were given at the beginning, which was 2 sin x degrees plus 5 cos x raised, that is equal to K, which we found out to be root 29 sin x minus A, where A is 291.8 degrees.